All right, guys, this is going over the Unit 6 review. I'm going to do this in a couple of different videos. I'm going to try and get through as much of the non-calculator stuff in one as I can, and then go over the, or the calculator stuff and then go over the non-calculator stuff. So we're going to start just at the beginning. This is finding key features with technology. So we're going to be using Desmos. So what you should be doing is inputting, let me split my screen here for you. The equation into Desmos. Okay, so for number 1, that is y equals 7. And you need to know where things are on the keyboard. Absolute value is here of 3x minus 10, and then minus 8 outside. Okay, so we want to know domain and range, vertex, if it's a function that has a vertex. If it doesn't, you know, like where's the center. Increasing, decreasing intervals, and asymptotes if there are any. Now, you may want to make a note. I'll actually make a note here. Of course, my pen is not working. Every time I start a video, my pen doesn't want to work. Try this again. All right, so you may want to make a note here that the only ones that have asymptotes, the only functions are your log, exponential, and rational. Okay, so those are the only ones that are going to have asymptotes. None of the others will. Okay, now let me go back to get the Desmos. So if I look at this graph and I want to know, you can zoom in and out on Desmos. You click on it and it'll tell you the point. Okay, now your answer choices, like if this was a question that said what's the vertex of this, it's probably going to be written as a fraction and not as a decimal. But if you don't know how to convert from decimals to fractions, remember you can always just type in your answer choices that are fractions and see what they are as decimals. But we know that 0.3 repeating is a third, okay? And so 3 1/3 is 10/3. So that's how I'm going to write it. So I'm going to say that that's at 10/3, -8. Now that's going to help me determine my domain and range, because I know if you want to draw the general shape of it, you can. This is this V shape, okay? That vertex is a minimum. More specifically, it's an absolute minimum. It is the lowest the graph ever gets, right? That's not what I meant to do. We can look at it side by side. All right, so we've got the vertex and identified if it was a max or min. I know there's no asymptotes. So now that I know that vertex, I can give the domain and range. So this domain, absolute value domain, all real numbers always. It's left and right forever. Now the range, that lowest value, the y value is -8, and it goes up from there. So it's -8, including the -8 to infinity. And then your increasing, decreasing intervals, this graph from left to right is decreasing until it gets to that vertex, and then it's increasing. So I would say it's decreasing from -infinity. And when we give increasing, decreasing intervals, remember this is x values. You want to make that note. Okay, so the x value here is that 10/3. So it's decreasing until it gets to 10/3. And increasing, decreasing intervals are always parentheses. Don't use brackets for increasing, decreasing intervals. And then the graph turns and it's increasing from 10/3 to positive infinity. And that's it. That's all you needed to do for that function. Okay, so the one underneath that, you know what, since I've got absolute value typed in there, are there any other absolute value? No. Okay, so I'm good. I just wanted to go ahead and do the other absolute value since I had it typed in already. That's okay. All right, so 10, and then you square root of 2x plus 3, and then outside the radical minus 8. And we can see that graph here. Oops. Zoom out a little. There we go. So you can see that starting point there. So I'm going to click on it so you can see it. I guess this one won't, you just hover and click and it'll show. But it's at negative 1.5, negative 8. Let me change that color. Be consistent here. Okay, and that is a absolute minimum. It's the lowest this graph goes. So that means that my domain would be from negative 1.5 to infinity, because it's going to the right from there. I include the negative 1.5. And my range is from that point, the y value, negative 8, and it's going up to infinity, and I include the negative 8. Now the increasing, decreasing intervals, this graph, that's its starting point where it goes, it is only increasing ever. So there is only an increasing interval, and we use x values, so it's from negative 1.5 to infinity. It's increasing. There is no asymptote in this one. All right, I think there was another square root one. Nope, just kidding. All right, but there is a cube root. 2. If you need a root other than a square root, you click on functions. It's down at the bottom, and you get to type in whatever the root value is you want to see. All right, so we got a nice picture here of our cube root function. Now, there is not a vertex on a cubic or a cube root function, but there is that point of inflection, like that center where the concavity changes, and that's what we want to identify here. So actually, you really don't have to. I mean, you can see it because this is like vertex form of the equation or whatever, you could figure it out, but we really don't need it. You're not going to be asked a question about what's the point of inflection of this cube root function. So, and it doesn't affect the domain and range because it goes in all directions around that. So we'll just start with domain and range, which are both all reals. Cube root and cubic and any odd root or odd power, the domain and range are all real numbers. Okay, now this graph is left to right. It is increasing always. It doesn't change directions. So it is increasing from negative infinity to positive infinity. And that's all we need for that one, because there are no asymptotes and there is no vertex. And so we don't need to bother with the center. That's all right. All right, let's look at this log. We've got 3, and then if you go to functions button here, that's where you'll find your log down toward the bottom. Not all the way to the bottom. Here we go. So if you have a log base, you need this one that's log base A. If not, if it's a common log, you just click that one. But we need to put in that it's a base 2. And inside the parentheses is x minus 3 and plus 1. So logs, you can zoom out and see this if you want, have this general shape. Okay, they are the ones that have the vertical asymptote Okay, unless it's been shifted left or right, the asymptote starts as the y-axis. It starts at 0. But we can see this has been shifted over. If you want to zoom in and see that value where it looks like it is, notice where it looks like it's flattening out or leveling out vertically here is at 3. And that's because of that -3 inside. Okay, so some of you won't even need a calculator for these, but you do want to be able to recognize it in the calculator as well. Okay, but you can also recognize it from the equation. So there is no center or vertex for this one either, but there is an asymptote. So this is a vertical asymptote. So I'm going to make sure we know that that's vertical. Okay, and so a vertical asymptote is x equals, because it goes through the x-axis, at 3. Now notice when we were drawing them, we drew dashed lines for our asymptotes. Those don't show up in the calculator. You have to visualize. There's this imaginary dashed vertical line here that the graph never crosses at x equals 3. So that means that the domain is from 3 to infinity, and it does not include the 3. If it's an asymptote, it's not included. The graph never reaches 3. And then the range is all real numbers, negative to positive infinity. Log, that's your range. No matter what sort of reflection takes place, all logs are going to have that range. Let's see. Oh, increasing, decreasing intervals. So this one, left to right, is increasing, but it is increasing from 3 to infinity. That's it for that one. Let's go to this other column. No other logs. Okay. So we've got a quadratic now. I actually probably should have put in the instructions here to identify what type of function it is, because you need to be able to do that as well. But there was practice with that at the end of the review as well, so it's not a big deal. Minus 4x, 10. All right, so we've got a quadratic. This is going to be a parabola. And we can see its vertex is at 1/2, 9. And you can write it as a fraction, 1/2, or as a decimal, it doesn't matter. And this is an absolute minimum. It's the lowest the graph goes. So that means that my domain, quadratic, all real numbers, but my range is from that y value, that 9 is the lowest it goes. So it's from 9 to infinity, including the 9. And then it is decreasing left to right until it gets to 1/2. So from negative infinity to 1/2. And then it is increasing from 1/2 to infinity. All right, now we've got a cubic. So the cubic function, cube that, and that's a 10. 7x. All right, so we have a cubic here that has got some changes in direction. This is not, this is like the center. This hasn't been shifted over if we were to figure this all out, but it does have a couple of vertices, a couple of changes in direction. And in this case, because this graph goes on forever up and down, we know that those are not absolute. Okay, so we actually have 2 vertices here if you want to identify them as that. And then we've got the center there, the x and y intercept goes through the origin, but we weren't asked to identify that, so that's okay. So there is a local or relative, remember those terms mean the same thing, maximum. Let's see where that is. Click on that so we can see those points. So the relative maximum is at negative 0.483 to 0.254. And then there is a relative minimum at 0.483 negative 2.254. And then that means my increasing, decreasing intervals. I'm increasing as the graph goes left to right, starts off increasing until we get to that maximum, which the x value is the negative 0.483. And then the graph changes to decreasing from that negative 0.483 until we get to this minimum, which the x value is the positive 0.483. And then the graph turns again and is increasing again. So I go back up here and I put a union, and then it's increasing from positive 0.483 forever, so to infinity. I did not give the domain and range of this one yet. Domain and range, this is again a cubic. If it's an odd power, its domain and range are infinite. So both of those are negative to positive infinity. All right, let's look at 6. So this one is exponential, meaning x is in the exponent. So we've got x minus 1 in the exponent. The base is 2. Why is it not putting the minus 1 up there? Minus 4. So notice I typed it in and then I checked and it wasn't in the exponent. So always double check before you look at your graph, make sure you've got it typed in correctly. So 2 to the x minus 1 and then minus 4 outside the exponent. Okay, so this is an exponential. Remember, this is the inverse of the log function. So it has a horizontal asymptote. Okay, and the horizontal asymptote is where it looks like it's flattening out here. So that's at negative 4 on the y-axis. So it's y equals. So that is horizontal asymptote at y equals negative 4. And you could tell that from the equation because it was shifted down 4. So the asymptote on the parent function that's at 0 has been shifted down 4. So y equals negative 4. No vertex or center here. Domain. Exponential is all reals, just like for, that's the range for log, because remember they're inverses. So it doesn't matter how this exponential is reflected. It can be reflected over the x, it can be reflected over the y, but the domain's going to, left and right is going to go on forever. But the range goes from the asymptote to infinity in this example. If it had been reflected down, it would come from negative infinity to the asymptote. So pay attention to reflections as well, if you have a negative value being multiplied. And then increasing, decreasing intervals, this graph is increasing from left to right forever. So all real numbers, it's increasing. All right, and then last but not least, we have a rational function. 1 over x plus 4, and then outside that fraction is a minus 2. So remember, rational functions have 2 asymptotes. They have the vertical and the horizontal asymptotes, normally at y equals 0 and x equals 0, but this graph has had some shifts. It's shifted down 2, and we can see that. Okay, so this asymptote that both of these curves approach horizontally on the left and right is at negative 2. So there's a horizontal asymptote at y equals negative 2. And then there is a vertical asymptote. And we can see visually here that's at the negative 4. And you can see in your equation, it's what would make the denominator 0. So you set the denominator equal to 0 if you were doing it by hand. And negative 4 is what would make this 0. And your denominator cannot be 0 because you cannot divide by 0. So we've got our asymptotes, which tells us our domain and range restrictions. Our domain is everywhere except -4. Left to right, this graph goes on forever, except there's this break at -4. So that's written with the union like that. Same thing for range, down and up forever, except for that break at that horizontal asymptote at -2. So there you have it. Okay, so that is the first section of the review. Finding key features with the calculator, with technology. Now these last two here, you don't need a calculator for, but this type of question could show up on the calculator portion. Remember I said it doesn't mean you need a calculator for every question on it, you just get a calculator for the whole test. So we talked about symmetry. The three main types of symmetry we discussed were the x-axis, y-axis, and origin. So is it symmetric about the x or y-axis means can I fold it on one of those axes and everything would match up. Okay, origin means if I rotate it 180 degrees about the origin, okay, that it looks exactly the same. Looks like it was unchanged. Now the difference is some people have trouble picturing the rotation. So remember I also said the origin symmetry, you could also picture it as folding over both axes. If I folded it over the x and the y, would everything match up then? Okay, so this first image here, if I folded this over the y-axis, I did not draw a straight line, but you get the idea. If this is my axis of symmetry, all of these points would match up. You can see this one is at +3 and at -3. 3, 0, -3, 0. So if you change the sign of the x value, all the points line up. And they do. So this one is symmetric about the y-axis. Which means we talked about odd, even, or neither functions. If it is symmetric about the origin, it is odd. If it is symmetric about the y-axis, it is even. So this is an even function. Now in number 10, this graph, if I folded it over the y-axis, they would not align. If I folded it over the x-axis, they would not align. But if I rotated this graph around the origin, oh, you know what? That is slightly off the origin. So technically, I didn't even catch that. Technically, that point there is not at the origin that it goes through. So really, this has no symmetry. But when I included this, I thought it was going through the origin. So we're going to pretend, so I can show you this as an example, that this graph in the middle, this curve, goes through the origin. Okay, so just play along with me on that. So if I were to put my finger here, my pencil here, and turn this paper upside down, it would look exactly the same. Okay, this curve that was in quadrant 3 would appear up here in quadrant 1 and vice versa. And this curve that's decreasing left to right in the middle, if I flip it upside down, it would still be there decreasing left to right through the exact same points. Okay, so this one is symmetric about the origin. And that means that it is odd. If there is symmetry, but it's not origin or y-axis symmetry, the function's neither, okay? Or if the graph you have is not a function, it fails the horizontal, or excuse me, the vertical line test, then it's not even or odd, okay? To be even or odd, it has to be a function, a one-to-one function. Okay. All right, let's see if we can get through this page and then I'll stop this video. So this one I think was confusing to some people. You would need to go back to what we talked about for transformation rules, because this is not some function we know. This is just a random sketch just saying, hey, this is the original function. This is what we're starting with. So I'm going to call it f of x, or you could do g of x, h of x, whatever. Okay, so I'm going to call this f of x. It changes into this. I need to be able to write a transformation equation describe what's happened. Okay, now, so I'm going to, for the sake of reviewing with you, I'm going to write it in words as well. Okay, so this graph, this point that is normally at 0, 0 has shifted over 2. So I know it's gone right 2. Okay. It hasn't gone up any. The y value, it's still on the x-axis, but this graph has gotten taller. It's been vertically stretched. You can see the height of it was 4, and now the height of that is 8. 5, 6, 7, 8, yeah. Okay, so it's doubled in height. That means it's been vertically stretched by 2. Okay, now horizontally, let's see if there's any change. It was, the width was 6. The width is still 6. So it hasn't been horizontally stretched or compressed, and it hasn't been shifted up or down. So just those 2 transformations. So the transformation rules, if there is a vertical stretch, that's your A value, that's multiplied outside. So in front, it's being multiplied by 2. And then a horizontal shift happens inside the function. It's added or subtracted inside, and we have to remember that's the opposite. So to the right 2 actually shows up as minus 2. So this is what I wanted y'all to write. Okay, so it's a function stretched vertically by 2, shifted right 2. That's, you need to be able to read that and understand what that means. And if you go back to our notes on transformations, we did some like that. We talked about the rules. I think we used A and B, or A and C or whatever letters instead of numbers, but I think we may have done some examples with numbers too. All right, so we're going to do the same thing here. So this is f of x, what I started with. Now, how has it changed? Okay, the starting point here has shifted up 2. So up 2. Let's see, the height was 4. The height is still 4, so no vertical stretch here. But this time, the width was 6, and now the width is only 3. So this has been horizontally compressed. Okay, and it hasn't been shifted over any, and it hasn't been reflected. Okay, so horizontally compressed by 2. It's compressed, it's half the size. So it's compressed by 2. So that means in my function, we need to remember where that shows up. Okay, so the shift up shows up outside. So that's plus 2. That's outside the function, not inside. Okay, the compression horizontally is inside. So remember here, just remind you, a vertical stretcher compression was multiplied outside. A horizontal stretcher compression is multiplied inside. Okay, we're calling that the B value. Okay, now, just like horizontal shift, it's the opposite, because to the right was minus 2. It's always the opposite of what you think inside. You have to remember the same thing applies, and we talked about it in the notes. For horizontal compression and stretch, you would think a compression means it's a smaller value, like a 1/2 here, but it's actually a 2. This does not mean it's 2 times wider. It means it's 2 times narrower. Okay, it's compressed by 2 to have that B value of 2. If it was 2 times wider, like if it had gone from 6 to 12, that would be a 1/2 there. Okay, so it's the opposite of what you would think when it's inside. So remember, inside the function is horizontal changes, outside the function is vertical changes. So that's what we were looking for there. And then last but not least, this one has been reflected. So a flip over the x-axis. Okay, the starting point has shifted right 2. And let's check the width and height. So it started out height of 4, width of 6. This has height of 4, but the width is only 3. So that's the same rule we looked at here. So that's going to be a 2 on the inside for that. And the right 2, that's going to be the same rule we looked at here. That's going to be the -2 on the inside. So these are both horizontal changes. So right 2 is -2. And multiplied by 2, but inside. But I'm going to kind of break it down like this, because that's still inside the function if I write it like that. And I can see it nicely. Now, don't forget the negative for flipping over the x-axis goes outside. Now, if you wanted to simplify inside there, that could also be written with distributing that 2. So that would be 2x minus 4. But that way it's harder to see. It looks like, oh, right 4. It's not right 4 because of this 2 was distributed. So seeing it this way, you can see that's right 2 compressed by 2 reflected over the x. Okay, but you may also see it written this way. So both of those are correct. All right, I'm going to stop this video there. And then if you have questions past this one, you can check another video.